All right. Does that work? Yes. Hi, welcome everyone. We are gonna start the meeting. Just so you know, the meeting will be streamed live. So right now everyone's hearing the chatter. The meeting's going to be streamed live on YouTube. So same as the Royal Academy of Sciences a few weeks ago, you'll be able to catch it at least for a few hours. If you missed something, the slides are going to be posted online. You should have received an email if you're a panelist about how to share your slides. If you don't, come and talk to someone on the local organizing committee. And for the first session, Martin is chairing.
Okay, everybody, thank you very much for showing up on time. Just get this first session straight underway. We're going to start off by hearing from Natalie.
Hi, good morning, everyone, and welcome to Berkeley Lab. So this is really a pleasure to be hosting you here for this spectroscopic future meeting on how to plan the next step beyond what's currently happening and see all the great science that will come out of it and that we need to get ready for. Just a few words about Berkeley Lab. Berkeley is a DOE-sponsored national lab. It's a multi-purpose lab, which means that physics is not the only area of research that it's focusing on. It's also doing a lot of work on biology, on energy. It also has a very strong engineering division with about 400 people, and we often have we collaborate a lot with our engineers and who help us build all the fantastic projects that we're working on. It's also a user facility. I'm just showing a few of them here, the Advanced Life Source, the Genomics Institute, NERSC, that all of you know about. Physics is only one of the 22 divisions, research divisions at the lab. It's, of course, the one that is hosting us here for the work on the cosmic frontier in particular, but it covers other areas as well, such as energy frontier, intensity frontier, so that's a lot of neutrinos mostly, and with cross-cutting themes such as theory, detector R&D, and of course, Berkeley Lab is also the host of the particle data group, and we're really proud to be really fostering all the activity on the PDG side. NERSC is one of the facilities that I mentioned, just a few photos here of the Cori HPC setup and of Promoter that you all know, love, and hate, probably, depending on how well it works on the precise day during which you try to access it. Just a few words on safety. So we have a lot of construction going on site. You probably have noticed it. And we also have a lot of pedestrians. So that makes traffic a little bit dangerous. You have to be careful. As a pedestrian, please use sidewalks and crosswalks as much as possible. Watch your step. We're on a hill, so a lot of steps going up and down. And be careful when you chat with your colleagues, not to miss a step. We have a lot of wildlife, which is great. Most of it is harmless, but don't pet it anyway. Some of it, even though it looks beautiful, just don't approach it. And if you spot a wildcat, just go back in a car or in a building. Don't try to befriend it. In terms of traffic, I mentioned it. With a lot of pedestrians on site, be careful. Don't drive faster than 15 miles per hour. And, well, respect the signs. It's going to be nice all week. No smoking on site, only in the designated areas. And please, this is extremely important, respect that restriction. We're also in an earthquake risk area. So if we're not expecting to have drills during the week, so if anything shakes, if you have furniture around you, the recommendation is to drop to the floor, cover under any piece of furniture and hold on to it so as to move with it. Here in the auditorium, that won't be easy, so just go outside and follow the directions that you will be given. And for any emergency, the usual numbers are here, 911 for any life-threatening emergency, and otherwise for any other event, 6999 is the number to call. And with that, I will start on the science side of this workshop. And I'll give you some brief updates on DESI and then a few steps on what's happening thereafter. And that will lead into the following talks from David and Kyle. So starting with the year one DESI results. So DESI in a nutshell, let me see if I can see my own slides. DESI, in a nutshell, it's an entirely refurbished facility at Kitt Peak in Arizona. The photons first bounce off a 4-meter diameter mirror, go through a corrector that allows us to obtain the field of view that we designed with 8 square degrees. Then the light goes to the primary focal plane, which is really the jewel of DESI, with 5,000 robotic fiber positioners. Each of them guides the light 40 meters down to the spectrographs. We have 10 spectrographs split in 3 different bands covering the entire visible range from near UV, and that's the limit that is required to reach the Lyman alpha side of our study, and up to the near infrared, which is the limit that constrains how high we can go in redshift with the emission line galaxies. With DESI, we aim at covering over 5 years roughly 40 million galaxies and quasars with an uninterrupted redshift range from roughly 0 up to above 4. And we have 4 different categories of targets to do so. In the nearby universe, we aim at using about 13 million bright and puffy galaxies. Then going into the slightly more distant universe, we're focusing on 8 million luminous red galaxies. Going even further back, we're using emission line galaxies, which are young blue galaxies with a strong O2 doublet that allows us to determine the redshift extremely well. And then the most distant universe, we have to use the brightest objects that are out there. And with DESI, we're using quasars with the aim of collecting 3 million quasar spectra that we'll use in 2 ways. Up to a redshift of 2, the quasars are still numerous enough that we can use them as direct tracers of the matter. And beyond that, there are very few quasars, but the way we use them is as background lighthouses that illuminate the intergalactic medium, and the absorption in the quasar spectrum by the neutral hydrogen in that intergalactic medium produces Lyman alpha 4s, which is a tracer of the matter in the most distant universe. On your right-hand side, you have the goals that we want to be achieving with DESI at the end of the survey. So basically a sub% measurement of BAO in 3 different regimes of redshifts. And on the RSD, we expect to have a total of 21 independent measurements up to a redshift of about 2 with a medium precision of 5%. The results that were just published now a month and a day or a month and 2 days ago, based on the first year of DESI data. And the plot that you have at the top right is the footprint that was covered with these first year data sets. So the regions in gray are the northern and southern galactic cap that we aim at covering at the end of the 5-year survey. And all the colored dots is what we've been observing already with DESI. In red is when it's complete with all the passes that we want to have on a given area of the sky. And when it's only blue, it means that it's only one pass and we'll go back to those areas. So you see that with year 1 really covered pretty well the equatorial region of the northern galactic cap. We have a large coverage of almost all the footprint, but with only a single pass. So there's a lot more to be coming with the future observations to improve the completeness of this coverage. Overall, if you just want to have a quick number, basically in year 1, we have about 25% of all the ELGs and 45% of the quasars compared to what we'll have with the full completed survey. So the data that we provided were analyzed with a fully blinded analysis, and that allows us to have really results that are robust and that we can be confident in. And the main goal was, of course, to avoid confirmation bias as much as possible. The systematics uncertainty that we have on this first year of data are shown here, and it's really, it's much smaller than the statistical uncertainty. So that means that DESI is really statistically limited and not systematic limited, and that's very important for also going forward with the future DESI data. Globally, on the first year, the part of the systematic is only 5%. It only increases our global uncertainty by about 5% compared to the statistical only uncertainty. I mentioned the Lyman alpha 4s, so just a slide on what that is. On the top, you have a spectrum from a quasar. The big peak that you see is the Lyman alpha emission peak of the quasar, and it's of course redshifted to the redshift of the quasar, and everything leftwards of it is bluewards of it, so it's less redshifted. And there are the noise that you seem to see in that spectrum is actually the forest of absorptions from neutral hydrogen, also in Lyman alpha, but less redshifted than the redshift of the quasar because that's along the line of sight. And that is specifically what we're using when we're talking about analyzing the Lyman alpha forest. This is the region of the spectrum that we're using. We're using Lyman alpha forest lines of sight in two ways. On the left-hand side, that's the standard Lyman alpha autocorrelation, where we autocorrelate two lines of sight and the absorptions in these two lines of sight. And that gives the correlation function that you see at the bottom left. But we can also use the information in the Lyman alpha lines of sight cross-correlated with the locations of quasars. And this is what illustrated on the right-hand side. And here you also have a correlation function, but because in the Lyman alpha forest, it's absorption, so it's a negative bias, whereas the quasars have a positive correlation bias, the product of the two gives you a trough in your correlation function instead of a peak as you are used to seeing. And so we've done both with the DESI year one, and in the center, you have the result that we obtain on the alpha parameters, which are the shift of the position of the BAO peak compared to where we would expect it to be with the fiducial cosmology that we applied. So you would expect it to lie on 1 if the fiducial cosmology were the cosmology that you would recover. And here you have the contours obtained in blue for the Lyman alpha autocorrelation and in dashed for the Lyman alpha cross-quasar cross-correlation. And you see that these two determinations, which are to first order independent, actually agree very well with one another. And in red, you have the combined result, which is the most constrained one. We also studied BAO with about 6 million galaxies and quasars, and this is a plot that illustrates all of that information. So the BAO information comes in twofold. Across the line of sight, you have a determination of an angular diameter distance, or an angular, the BAO comes as an angle on the sky, which translates into dm of RD. Across the line of, along the line of sight, sorry, you measure the BAO as a delta Z, a size in redshift, and that correlates to the H over RD. So you have two independent measurements from these two pieces of information. And so what BAO is mostly sensitive to is omega M and H naught RD. You can also, and this is actually what the plot on the top right illustrates. You have for each of our tracers, so several LG tracers, the BGS tracer at the lowest redshift. Then we have 3 LLG bins, 2 of them combined here as in red. And then the highest redshift LLG bin combined with the lowest ELG bin because they overlap in redshift. That's what's shown in purple. Then the ELGs, quasars, and the Lyman alpha. And what you see here is that all of these independent measurements agree extremely well with one another in these two parameters, which are the parameters that will determine the best. And so given their agreement, we can also combine them all. And this is the tiny black ellipse that you can see. And on this combined information, the aggregated precision is of 0.5% on the combined isotropic dV over RD BAO scale. You also have on the left-hand side that dV over RD as a function of redshift for each of our tracers. And you see here compared to a value of 1, which is our best lambda CDM fit. And there's a very good agreement with a lambda CDM cosmology. I told you that we, with BAO, we're sensitive to H naught times RD. So if we have a way of measuring RD or determining RD or constraining RD, then we can measure H naught. And so this is what is done on this slide, where RD has to come from another probe. So on the top line, we used the information from Big Bang nucleosynthesis, where we can determine omega B, and that gives us RD. And with that combination, we're able to constrain H naught to about 1%, 1.2%. we can add further additional information, such as theta star, which is the Planck angular acoustic scale. And with BBN and theta star in addition to DESI, we can constrain H0 to 0.9%. And then on the plot on the right, you see in bold blue the two measurements that we have with DESI. And you see that they compare very well with what was obtained previously with BAO from SDSS data. And they're also in good agreement, give or take 1 sigma, with the Planck measurements that are illustrated in orange. However, they are in tension with the shoes measurement, which is shown as the bottom green dot at the highest values of H0, and the disagreement between the tension between the BAO measurements from DESI and shoes is at the level of 3.7 sigma. The main goal of DESI, that's in its name, it's a dark energy spectroscopic instrument. So the goal of DESI is really to determine dark energy and to understand what dark energy is made of. This is the first slide on dark energy. Although I said before, the measurements are also in good agreement with lambda CDM, but going beyond that, we can try to constrain the equation of state parameter W. And so this is showing W as a function of omega m. With DESI alone, we can constrain W to a precision of about 15%, and the value that we obtain is in very good agreement with -1. There are other probes that also study dark energy, and they are also shown in this plot here. These are cosmic microwave background with Planck or supernovae data. We have currently 3 independent sets of well, not independent. We have 3 sets of supernovae data, 2 spectroscopic data sets, the Union 3 and the Pantheon Plus, and 1 which is a photometric supernova sample, which is the DESIR 5 sample. There are a lot of supernovae in common between Pantheon Plus and Union 3. The results that they obtain are still not in agreement totally, but that's a story for the supernovae people to work on. So we didn't take sides in DESI, and we're showing the results with all 3 sets of supernovae. And what you can see here on this omega plane is that all these 3 data sets, supernovae, CMB, and BAO, are in very good agreement. So we can combine any of the supernovae data sets with the other 2. And that's what is shown in the on the left side here, where we combine DESI, CMB, and Pantheon Plus, for instance. And that significantly strengthens our constraint on W, which we can now constrain to 2.5%, and still in very good agreement with -1. But that's assuming that W is a constant and does not evolve with time. Given the precision that we achieve with DESI and given the level arm in redshift that we have, we can also try to go beyond an average equation of state and have study our possibility to constrain a time-varying equation of state. So this is what we do here. We use the parameterization, the CPL parameterization, which expresses W as a simple linear equation with a fixed term and a time-varying term, WA. We show on the left and on the right-hand side here in the plane WA as a function of W0, the results obtained by Planck plus CMB lensing in this with this parameterization. So whether we use Planck alone or Planck and lensing give the green and blue contours, which you can't distinguish on this plot because they overlap extremely well. So it's really the big fatty area here. In addition, we show what DESI BAO alone gives, which is the dashed curve. There's very good agreement between the 2. We combine them, and that gives you the orange region that you see here, which gives a determination and a pull away from W of -1 at the level of 2.6 sigma, just with BAO from DESI and CMB, which is Planck, and CMB lensing. Now, we've mentioned those supernovae data sets, and we can also, therefore, combine this BAO plus CMB with any of the supernovae data sets that I've mentioned before. This is what is shown in the plot on top right here. And you see that depending on which data set we use, we have a pretty tight determination of W0 WA, whose pull away from W of -1 depends on the supernova data set that you're using and ranges from 2.5 sigma with the Pantheon Plus up to 3.9 sigma with the photometric sample from DES. And just taking the same plot as the one I've shown before here, so dV over RD as a function of redshift or look-back time, same data points as I've shown before, but in addition to the best fit lambda CEM, what we're showing here is in dashed curve, the best fit not WA CDM model from DESI, and you see how it fits the dV points better than a simple lambda CDM model. So this is for DESI year 1, but there's a lot more coming up. DESI is not only dedicated to dark energy, but it will also do not only BAO, but will also do an RSD study. The goal of that is to measure F sigma 8 and therefore be able to constrain modified gravity models. On the bottom plot, you have what we aim to achieve with the full 5-year survey. We're also aiming at studying non-Gaussianity through the FNL measurement. And so this is the power spectrum that we want to be measuring, and just here illustrating what it gives as a function of scale. These 2 studies are still blinding, but you can expect to hear from them in the next few months. Now, DESI has a tendency to like to stop its collection of a given year with very specific events. So the year 1 ended when the Contreras fire swept through the observatory. And then we decided to go ahead with about 3 years. And the decision of when to end the collection of the 3 years data sample was made when we had a major fiber rock failure. So this is the 3-year sample. But don't worry, despite these events, DESI is doing amazingly well. We have 3 years of data in the can. So that means that we already have 30 million spectra of galaxies and quasars. The survey is still 5 months ahead of schedule, despite the various events that are making the life interesting in DESI. This is the footprint of the 3-year sample, which you can compare to the one I showed before. You see that the coverage is much more complete. There's a lot more area that is shown in red here, which means that we have all the passes that we aim at obtaining on this particular footprint. And we also have a very much nicer coverage in the southern galactic cap, which was barely at a single pass in year 1. We, with this year 3 sample, we really hope to enhance the scope of DESI compared to year 1 in different ways. So this is a summary of what we want to be doing with the 3-year sample. Go for improved precision and robustness of our clustering. And so that means that in addition to the 2-point studies, we want to use higher order statistics for galaxy and quasar clustering. Alcock-Paczynski effect also in Lyman alpha, which was not used so far in the key project. We're also having a global study of the population of tracers that we're using for a better understanding of their properties and how they can impact the cosmology that we infer from them. We also plan to use new techniques, and in particular, not just BAO alone from DESI, but cross-correlation with data sets from CMB lensing to measure sigma 8, or with galaxy lensing as well for better constraining of the RSD nuisance terms. And on the low redshift regime, where we're limited by survey volume, we aim at using peculiar velocities to improve the precision on systematics for RSD. And we're also using the bright time with a survey of spectra to study the mass distribution in the Milky Way, and that can be used to study dark matter models. So beyond DESI, this is a sketch of the timeline as we see it today that evolves a lot, not quite on a daily basis, but almost. So DESI is on the left-hand side here. That's a 5-year survey. We are discussing an extension that we're actually in the process of discussing with DOE and making sure that it happens up to December of 2028, after which we aim to go into a new survey, DESI 2. So that's the same instrument, but with a new scope of research for 6 years. And during all that time, we will be preparing for a future spectroscopic survey, so whose R&D is already begun, and that we aim to be leading into construction and commissioning for a full spectroscopic stage 5 survey that would be able to use all the input data from LSST in order to get its targets. So DESI extension is illustrated here. The actual scope of what we'll be doing with it is still evolving, but a very good possibility is to use an extended footprint, as is shown in blue here, going further down in declination. And that will allow us to improve the precision that we obtain by having additional footprint, and also increase the overlap with the southern observatories for all these cross-correlation studies that I mentioned. We can also increase the number of passes over the existing footprints in order to improve the completeness, in particular in some of the targets, such as the ELGs, which come at lowest priority in DESI and have a lower completeness than the rest of our sample. Beyond DESI, I have only a few minutes left, and there will be 2 more talks on that, so I will go extremely fast. DESI really focused on dark energy. There are a lot more that we can do with spectroscopic surveys. We can extend the scope on for modified gravity by going to smaller scales. And there's a big area also where we can do much more than what we're doing with DESI, is on this high redshift regime above, typically at redshift of 2 and above, to study inflation through non-Gaussianity, through clustering studies, as well as constraining neutrino masses and studying the possibility for light relics that would also affect the clustering measurements in the galaxies. So DESI-2 is a 2-pronged program with a low redshift survey, high density for all these cross-correlation studies that I mentioned, and beating the cosmic variance. This is really the main goal of the low redshift survey, in addition to the dark matter science that I mentioned with the stars. In the high redshift regime, this is really aiming at inflation and non-Gaussianity. That's where we have more linear modes. So that's also where we are still more correlated with the initial conditions. And that's one of the great advantages of going to higher redshift. So the challenges are different for these 2 samples. And I won't go into the details here, but happy to discuss those challenges. And then even beyond DESI-2, I mentioned the SPEC-S5 project. This is a project that was presented to the P5 panel now over a year ago, which is the panel in the US that determines the roadmap for the next decade on particle physics and cosmology. And we're really happy to see that there was a strong endorsement for such a future survey in the P5 report. And just taking here one of the quotes from this report. And so that gives us very good hope that we can get started on construction of such a project in a few years. But of course, with a lot of work to be done until then on R&D, developing all the other projects. And you'll hear from Kyle and David about all the work that is going on this side. And so I'm just showing here my conclusions. We just have the publication of the first-year data sample from DESI and the results that are coming out from the BAO study. There's an interesting hint for time-varying dark energy. And so we're really looking forward to the future studies that we have with all the data that we still haven't analyzed to see what becomes of this hint. And there's a lot more to be expected from DESI, but also beyond DESI. And this is why we're here during these 3 days to discuss all these options. And I'll be really interested in hearing all the ideas that you have to develop this field further. Thank you for your attention.
Time for a couple of questions.
Yeah, I have a very naive question. You mentioned the power spectrum information is still blinded, but also we know there's still current constraints on the neutrino mass. I'm wondering, like, do you actually use the power spectrum information to constrain the neutrino mass, or it's more from just omega matter?
Well, here in the data that we publish, it's only a BAO result. So we haven't used the power spectrum in there. But that's something that we will go back to once we have the RSD studies. And definitely we will be looking at the neutrino aspect of those results very soon. But so far, we haven't used the power spectrum. It's only from the correlation function.
I see. Good. Thank you.
The BAO information.
So looking back at your slides, are the constraints on omega naught omega A model largely coming from LRG data?
So you want to use, yeah, here, for instance, on the left-hand side, for instance, that's,
yeah, this one. So I was asking if the constraints on omega 0 omega A model are largely coming from LRG data here.
so we have investigated a lot where that constraint could be coming from. And in particular, indeed, we have data from the previous survey, SDSS, which shows some deviation on the low redshift points. And so one of the tests that we did was to replace the points at redshift below 0.6 by the SDSS points. Where there's a good reason for that also is that DESI is already more constraining at high redshift, but currently the power of the constraining power from SDSS and DESI is comparable at the low redshift below 0.6. So we replace all points below 0.6 by the SDSS point, and we still see a tension, a small deviation from W equals -1. So it's not coming only from that point, which seems to be deviating a little bit more than the others. It contributes, definitely, but it's not its only contribution because we can replace the lowest redshift bins by SDSS data, and we still have a comparable trend. So it's part of the explanation, but certainly not all.
Okay, there's no further questions. Let's thank Natalie again. Okay, next we have David Schlegel and then Kyle, and back to David.
Yeah, we
Okay.
jiggered the schedule a little bit.
Okay.
Okay, we're gonna tag team. Let me just ask first, lights out, is that okay right now? Everyone's still awake? We're good? Because cosmology, it's a fast moving field. Natalie was just here. She was showing us results from 4 weeks ago. That's old news. You have to get with the program here. So we're gonna talk about now the stage 5 spectroscopic survey. So, you know, DESI's great, but we'd like to do something large and ambitious. That was a joke. My jokes aren't very good. Okay. Okay. Let me just a little bit of history here because I think it's of interest. A lot of these spectroscopic surveys in recent decades, let's say, have been designed around the question of dark energy. And way back in 2005, there was this dark energy task force advising the various agencies, saying what we should be doing in the coming years as far as different stages of experiments and what they would measure in dark energy. So there was the SDSS, that was a confirmation of the measurement of dark energy from BAO. The next SDSS, BOSS and EBOSS, that was really designed around BAO as a probe of dark energy. And then stage 4 is DESI, and that's, you know, this more ambitious probe of dark energy, redshift 0 to 3. And I should say, this roadmap was set out 20 years ago. We've actually gotten there a lot faster than most of us expected. Like, maybe not as fast as you'd hope, but faster than we would have realistically expected. So we've actually run out the end of this dark energy task force at this point. So at this point, we're just beyond the horizon of everything discussed. So the stage 5 spectroscopy, it's beyond DETF, but it's also beyond the physics that we were talking about at that time. Okay, so this project, as we're discussing it, is primarily designed around exploring early universe physics and our understanding of inflation. It will actually address questions of dark energy and dark matter. And the way that it's doing it is building the largest three-dimensional map of the universe. And so this is just in some co-moving-esque coordinates. You can see we're getting a much larger map. Okay, and then the stage 5 experiment, as designed, we're looking at something that has approximately a 10 or 15 times survey power compared to DESI. And DESI right now, of course, is the state of the art. And what we're going to get to here is we really need the theory development. This is your opportunity to really affect exactly what this project looks like. So right now, we have a design, we have some goals that we've written down, but you should think, maybe you're smarter and more knowledgeable than the people who wrote down these goals. Okay, so this is your opportunity to really affect what this is going to look like. Okay, we did at least shepherd this through the processes here in the US. So the SNOMAS process that did endorse the science, and then P5, which recommended Spec S5 in particular. Okay, I'm not going to read through all this, but in the P5 endorsement, it endorses essentially this roadmap of experiments from DESI to DESI 2 that Natalie was just discussing, and then Spec S5. Trade off here? Yeah, okay.
Okay, so we'll trade on and off. As we do so, does anyone have any questions on the process so far? We can always stop at each chapter in this presentation. Okay, so the question is, what is the current status of DESI 2? The current status is that we have operations funding for DESI for roughly a 5-year program that was established with initial science goals. We have to go through a review in about a month and a half where we're going to ask for an extension for 2.5 more years that Natalie presented. That has not been approved, but we are being reviewed on that case very shortly. And then we have to go through the process and advocate for an extension of what we primarily operations for DESI 2. It does not have to go through critical design as long as there's no major construction. And the plan right now is to have no significant construction or upgrades to the facility. So basically keep it roughly as is with some 10 to 20% improvements that we think we can do for a reasonable cost that prevent it from going to construction. And then operate at roughly the same cost that we're operating DESI right now. Anything else? Okay. So I'm gonna outline what we see as the baseline science goals, and I'm gonna lead into the flow down to requirements. Keep in mind that I'm saying baseline as these are what we've come up with given our current knowledge of the field. These are kind of the low-hanging fruit. But again, as David and Natalie both inferred, we are gathering information as we go through this process. Roughly speaking, you can break the categories into 3 different components. The first is inflation in early universe. The second is dark energy, and the last is dark matter. Those are presented in chronological order of the universe's evolution, but they're also presented in what we see as the order which will set the survey design and the facility requirements. The facility requirements are primarily going to be driven by this first bullet point. So what is this first bullet point? Inflationary physics. I think we have pretty good knowledge that inflation is an important stage in cosmic evolution. The information we have up to date is limited primarily to some of the stage 3 measurements around like the primordial tilt, the spectral index of the power spectrum. We have upper limits on the tensor to scalar ratio coming from polarization measurements from the CMB. We have this kind of generic model for inflation where we know because NS is not equal to 1, we know it's not exactly scale free. We know gravity waves are small enough that we haven't detected them yet. Some of the simplest models for inflation have been ruled out, but there's a very large parameter space still remaining on describing the inflationary field. In theory, parameter space both in theory and in actual observables, as I'll get to in a second. So when we look at the observables that are possible in characterizing the inflationary epoch, we know a lot about the tensor scalar ratio. That sets the energy scale for inflation. And of course, that's measured in CMB. It's really the primary science driver for CMBS4. That's going to give us pretty good insight into the rate of expansion in inflation and whether or not there's a detection. If there is a detection, it will really provide evidence that gravity is quantized. But Spec S5, that will extensively explore inflation beyond that metric, that one observable. The topics that are most commonly discussed are non-Gaussianity, but also another is primordial features. And Spec S5 will give us great insight into both of those. So on the non-Gaussianity side, that carries information about the actual physics of the inflaton fields. There is information, of course, from CMBS4, but through measurements of higher order statistics, more modes, et cetera, Spec S5, a spectroscopic survey, offers a significant amount of additional information. Some ideas, again, just hitting on rough topics of this, how you get more insight into the inflationary epoch. With non-Gaussian measurements, you can get a feeling for the number of fields present during inflation, the state of the inflaton fields, and also interactions that may have taken place at the time of inflation. So the next category in which we can broaden the observable space of inflation are on primordial features. Broadly speaking, these are deviations in scale invariance, and they are actually well motivated from current particle physics. Some ideas that can produce primordial features bulleted out here, but the basic idea is that they're best measured by Spec S5, and we'll have a dedicated session tomorrow discussing this. Okay. Now, inflation, of course, is the earliest epoch, but there's also physics that can take place at very early times immediately following inflation. It's typically characterized by light relics. These are particles that may have been in thermal contact with the standard model at very early times, but fell out of thermal contact. That would make them very low mass, weakly interacting. The second bullet point is a cut and paste error. Ignore that. But I'm just seeing this now. The idea is if you can get down to measurements of N effective around like the 0.03 level, you can really start probing some of the earliest epochs of cosmic history. And that can basically be done through CMB and large scale structure. Now, large scale structure covers all the cosmic evolution from that time on. There must be other physics present as well that can be explored with such a survey. We've covered some of the basics, but we're really also holding this conference to gather other ideas in addition to what we've shown so far. Okay, so the question is, what is best measured by layer scale structure at these high redshifts? To give you a little bit of insight into what data will look like in a future survey, I present first the power spectrum measured in the Sloan survey. You can see the error bars on the scales of interest here are quite large compared to even the baryon acoustic oscillation features. They're presented in the light blue. Those are the SDSS measurements. And you can see how the power spectrum responds to perturbations in our cosmological parameters presented here, and how those perturbations, what's the scale of those perturbations relative to SDSS error bars. This is really meant to be conceptual. These are not necessarily milestones. It's really meant to demonstrate the effect. So for example, FNL local, if I look at a value of 10 and a bias equal to 3, I see what's presented in the dashed line here. You can see in the power spectrum, deviations primarily at small k or large scale. You can also see the effect of delta N effective equals 0.1. You know, again, just for demonstration, this is about 4 times bigger than the threshold I showed a few slides ago. But you can see in the dashed yellow curve what a perturbation of this scale looks like relative to lambda CDM, where N effective is 3.04. And then likewise, in the blue is the response to a neutrino mass that's twice the minimal allowed mass in the normal hierarchy. So 120 millielectron volts. Again, we're able to make measurements at about this precision or better with current techniques, and can improve significantly in the future. Okay. So what will it look like in the error bars when we go to a future survey spec'd out by what we'll show shortly? Here, I now have to zoom way in on the y-axis because we don't have to set such a large dynamic range to cover the large error bars from SDSS. Here, presented in red, are the projected error bars as a function of scale for a spectroscopic survey in the future with properties I'll describe shortly. These error bars are purely statistical, derived from a Fisher formalism based on the survey volume and the number of tracers. Yes, we do not put any modeling uncertainties into this forecast. So that's been marginalized out. Oh, so that's why we see the error bar is increasing at small scale. Okay. Yes. Okay, so Martin made this figure. I didn't know I actually thought these were purely statistical based on Fisher forecast. I didn't know he had marginalized out so he marginalized out some of the EFT nuisance terms. And that, correct me if I'm wrong, that is why when we get to this nonlinear scale, presented in light in various shades of gray, we start seeing an inflation of the error bars. And that's because we're unable to disentangle the galaxy halo connection from the cosmology. Okay. And that actually is done under one particular assumption of bias, one parameterization of the EFT of our model. And those are things that are up for discussion in this conference. You know, what assumptions go into this and what modeling assumptions go into this. Okay. Other questions on this? Okay. Okay. So why use galaxies? The CMB and the galaxies both offer distinct advantages for measuring large scale structure. When I'm looking at the early universe physics, you know, the CMB is really nice because it's really working in the linear physics regime, and it has a really well-controlled tracer sample. It's one snapshot at one redshift. And you can understand the bias, you know, what's effectively the bias very well. Galaxies, the advantage is in sheer information content. But the fact that I'm going to 3-dimensional clustering, I get a vast increase in the number of modes accessible to constrain my cosmological model. So they really complement each other nicely. When I zoom more in on galaxies as optimal tracers, I'm targeting the redshift range 2 to 4.5. That's driven by observational constraints. There's kind of an area below redshift 2 where it's hard to get redshifts because of line identification. At higher redshifts, it's very hard to get redshifts because things get very faint. So that's what's setting the effective upper limit based on our target selection. This redshift range is a really nice sweet spot for cosmology because it's roughly where the volume per solid angle is maximized. So that gives my large number of modes I'm looking for. And the fact that it's higher redshift than what we've been doing in DESI also has the benefit that there's reduced processing of the density fields relative to low redshift. Okay, so this gives us a closer representation of the initial conditions, at least in the density field. There's some questions about the tracers we're using and the galaxy halo connection, and that's also a topic for discussion later this afternoon. Some of the challenges as we look to this redshift range, I would say that what we're really suffering from, or I don't know how to say suffering, we're contending with, that's better, as we're really at the limits of what's available in imaging data sets for selecting the targets in the first place. And getting redshifts of these galaxies is becoming very hard because they're very faint, and it's easier to identify things when they have an emission line versus when they're more continuum based and you're looking for absorption features against the continuum. So there's different classes of target in this redshift range are easier or harder to identify. They're also easier or harder to identify in imaging data. The other question I alluded to a few minutes ago is, as I go to this higher redshift, I get an increasing bias with the tracers. And to some extent, that may or may not mitigate some of the benefits of going into more linear regime for the density field. So that's a topic of debate, and that affects the forecast. The assumptions about that evolution of bias affect the forecasts that are being made for things like non-Gaussianity, et cetera. And in general, there's a bias term, but there's also, as I'll show briefly, there's some uncertainty in the impact of using higher order clustering or higher order statistics to constrain cosmology parameters. So that has not been included in our forecast or survey design so far. Beyond the inflationary side and the early universe side, the samples I described will naturally give us measurements of Bernoulli oscillations and redshift space distortions. So this will give us insight into dark energy. Here I show what the constraining power is in green for what we've envisioned as a spectroscopic survey at high redshift. The precision is well below what's required to measure the contributions from dark energy at this redshift range. Okay, that's shown here in the solid gray curve, dropping off of the redshift in a lambda CDM model. So we're really able to look for deviations against lambda CDM, even in this redshift range with the precision we're forecasting. Okay. The third case, probably done through a bright time program, but with the same facility, with all survey specification or all facility design driven by the high redshift sample, is a dark matter project mapping out the local Milky Way to very high precision, very high resolution. Here's a map of the Milky Way as we know it today with stellar streams. Stellar streams have offered one particular avenue into studying dark matter, looking for perturbations from interactions with low mass halos. With the spectroscopic survey we're talking about, we'll be able to do a survey at much higher precision in the 60 phase space, radial velocities, positions, and with Gaia and other astrometric probes, peculiar motions in the angular plane. The science drivers here are looking for the gravitational influence of dark matter on small scales at in the vicinity of the Milky Way. I show different forecasts for how different dark matter models will affect the clustering of matter on these small scales. And kind of the sweet spot is around these halo masses, around 10 to the 7, 10 to the 8 solar masses. Where you can see certain models predicting a change in the number density of these halos, or specifically the number density of where galaxies are forming in these dark matter halos. Okay. So those are the broad science drivers. Today's talks, as the day goes on, are geared around delving into these a little bit deeper, specifically around the high redshift range. So in the second morning session, there will be a discussion of theoretical modeling and higher order statistics. Here you'll see how EFT is applied to large scale structure, and also physics beyond the power spectrum. which I think is something that requires a little additional thought beyond what we've done so far for forecasting these surveys. And in the afternoon, there will be a dedicated panel to discussing non-Gaussianity with an introduction on the topic, and then a closeout on, the different connection between particle physics, dark matter, and context from similar work being done elsewhere, like the European side of things. Okay, so today's session is really meant to be an introduction to, beyond standard model as applied to large scale structure. And again, to remind you, everybody, the expected precision here is what we're expecting from a large scale structure survey at higher redshift. Are there any questions before I go to requirements? Christoph? Okay. Okay, so the question is, how do we decide on the redshift range represented? So I specifically said redshift 2 to 4.5. On the low redshift range, it's because the Lyman alpha emission line is not present in optical band passes yet. So we can't use that emission line to get a redshift. That appears around redshift 2. So that sets the lower bound. The higher end, we've at the moment penciled in redshift 4.5 as a limit. Without going into gory details, it is based on target selection constraints. There is a requirement to get to higher redshift. You have to use a different dropout. You have to use an R-band dropout. And we have not found good success, just empirically speaking, with our pilot studies in DESI of getting redshifts with those techniques. We are not sure that we can get the signal noise. When we run simulated data using target selection in that redshift range, we are unable to get the signal noise that we think we need to properly redshift the sample. That is not a definitive statement. Further exploration could be done. But at the moment, we've set that upper limit based on what we believe is a reasonable estimate of facility performance. Yes. So yeah, I'm sorry, that is exactly right. The limitation is exactly the spectrograph and not the imaging data. So these targets are present in imaging data through our dropouts. You don't even need blue filters to do so. You don't need the UV band pass. However, our simulations, when I said simulations, it's specifically within the spectroscopy, indicate that we do not generate the signal noise required to redshift them with enough efficiency. But it is on the spectrograph side. I totally agree with that.
Can I ask a related question? Before we move on from that previous plot, do you have any handle at all on what various, because in the STSS version of this plot, the error bars are touched so large observation system. Do you have any handle at all on how limitations in the imaging, how things fluctuate across the sky, difficulty selecting targets for dust might affect those error bars, like just or 2 or 3.
Okay, so the question is, have we included any forecasts for systematic errors or anything else for the precision that's presented here in terms of the signal noise on the power spectrum as a function of scale? The answer as of right now is we have not done so. I do not know what those numbers are from DESI yet. We have not unblinded our full shape measurements. And I also expect improvements to take place within DESI's modeling. So this is a big question for setting our science requirements, is how much to fold in, beyond statistical errors, but systematic measurements into the fray. Right now, that is not in the requirements, but it's something we've been asking ourselves over the course of the last few months. But I do not have a number for you. Okay, so that is an excellent question. The question is, how does something like Spec S5 compare to Sphere X, which is going to be launched shortly? I'm going to leave that as a discussion for the panel this afternoon. I'm going to take the easy way out. How about that? I can give you one quick answer is we have spectroscopy, which also gives us access to other physics beyond just FNL local. For example, features in the power spectrum. But that will be definitely a topic of discussion for this panel. Okay. So this should go shortly, and then I'm going to turn the floor back to David, who will tell you more about the facility. So we have this broad goal for what science we want to extract from the next generation survey. That's going to flow down into science requirements. Right now, I'll show a draft of those requirements. These will evolve, but they're a pretty good draft based on understanding of the facility and what we've done in target selection and spectroscopy so far. So the super high level that David introduced at the beginning was that this conceptual design is based on this idea of a 10-fold increase on this primordial figure of merit. Basically, we want to capture 10 times as many modes in the clustering of matter than what we were able to do with DESI. This is achieved with more volume and also by going to higher redshift, where you have access to smaller scales while remaining linear in your modeling. Okay. This redshift range, 2 to 4.5 that we've been talking about, Christoph asked about the upper limits. This is really what we see as the most accessible from spectroscopic surveys based on what we understand about the sensitivity of the spectrographs. When you go to higher redshifts, really likely requires another technique, like for example, radio surveys. Maybe we'll call that stage 6. Some intensity mapping programs have already been discussed, but not yet validated to the point where we can begin construction. Here, just to demonstrate, is the scaling of volume with redshift. You go to bigger volume because we're going further away. We all understand that. So the science requirements, this also gets to Adam's question about systematic versus statistical. Right now, it's all based on statistical precision. So we have this kind of multi-dimensional science driver, right? It's getting at the inflationary physics, but with multiple angles. It's really the idea of getting this comprehensive study of inflation and also early universe physics. That leads to what we're calling as the level 1 science requirement. And at the moment, the draft is that the science requirement is simply stated as a 10-fold increase in the number of Fourier modes relative to DESI. So that's our level 1 requirement. So from there, you can flow down to what's required to get that level of increase relative to DESI. And that's about the target density and the volume you're exploring. We can accomplish this with several different configurations. You can change the redshift range, you can change the survey area, you can change the number density. What I'm going to show here meets that condition. And the survey area is 11,000 square degrees. We chose that for a couple of reasons. One is accessibility to the platforms we're considering. The second is availability of imaging data in the lower redshift range of the sample, specifically with a medium band survey that we're considering. The requirements are number densities of about 8 times 10 to the minus 4 in the lower part of this redshift range, and about 1/4 of that in the higher part of this redshift range. That translates to surface density of about 5,000 and 1,000 objects per square degree. So considerably larger than DESI, about a factor or 2 larger than the surface density of DESI's targets, but much fainter because now we're all above redshift 2. So that's going to require most of this gain in survey speed is actually to chase the fainter targets. And this draft, as I said already, is informed by understanding of target selection, our ability to redshift targets in our science case, but it is still a draft. Taking these requirements to the full volume and also applying the survey to lower redshifts and the Milky Way, you get about 62 million galaxies at high redshift. You get about 130 million galaxies at low redshift. And you get about 50 million stars for studies of dark matter physics. Now, these forecasts were based on assumptions that may or may not be conservative. They may or may not be realistic. I think they're actually very realistic under the conditions we assumed. But what did we assume? We assumed single tracer. We assumed that the power spectrum is the only source of constraining the cosmological parameters. We use a formalism that's in this Saylor et al. Paper. It's on the archive. That was also used for the snow mass process. And this leads to specific forecasts on the cosmology parameters I'm talking about that are bulleted out here. So with the survey design I presented, we get 0.04 precision on net effective, 1.4 precision on the local form of non-Gaussianity. We did not present forecasts on other forms of primordial non-Gaussianity. The BAO and RSD are about 0.1 and 0.6% precision, respectively, in this high redshift range. That's aggregate. And the primordial features, you get about a factor of 4 improvement over what's going to be possible with DESI. Okay. So I'll hand the stage back to David, but before I do so, are there any questions?
Hey, so suppose you didn't have that high Z sample, the Z greater than 3.5, because it's challenging. How much sky area would you need to make up the volume?
So I can do that arithmetic from this picture right here. So it looks like the volume increases by what, about 20% as you go from 3.5 to 4.5. And then there's an argument about linear modes. So you can do, based on that change, you can make the estimate. There is sky available from LSST Rubin that's larger than 11,000 square degrees we're forecasting. So there is room to increase the area of the footprint. And there's other trade spaces, for example, layering targets of different densities and different redshift ranges across different areas of the footprint. So there are other trades that could be considered. So far, our indication is we can get redshifts to 4.5.
Can you just explain a little bit more what the 10x Fourier modes means? Is that linear modes? Is that just signal to noise of 1? What went into that statement?
So I'm happy to answer that. And Martin, if you want to give me more backup. So it is linear modes under a standard assumption of the evolution of the density field. I don't remember exactly what constitutes linear versus nonlinear, but it is linear modes, and it is set to be NP equals 1. So you count up the number of modes that meet those conditions, and you get a factor of 10 increase in what we presented at that NP equals 1. Or signal noise equals 1. Any other, and there's, you can, from there, it's specifically spelled out in, I believe, the Saylor et al. Paper or one of the snowmass papers. What constitutes linear? Yes, so the dark matter targets, the question is, what are the targets for the dark matter program? That would be observations taken during bright time, and they're all stars in the Milky Way, and you have access to basically the outer extremes of the Milky Way halo, about 100 kiloparsec. Okay, David, you ready?
Good. And maybe we should turn the lights back on. I don't like the symbolism here of sitting in the dark.
I can turn them on. I couldn't see the screen.
Okay. All right. Well, I will stay in the dark. We'll figure it out over the coffee break. Fine. Okay. So I'm going to tell you more about the implementation as it's planned right now for Spec S5. The way you should view this is this is really a lower bound of what we would do. If you go back to 2010, there were the original white papers for DESI, and then you can ask what was actually built and what was the survey. And it was better in every respect from those white papers in 2010. Okay, so here for Spec S5, this is if we had a bag of cash right now and we had to start building, what would we do? And I'm going to tell you what we would do. Fortunately, we don't have that bag of cash yet. So that gives us the trade space to actually figure out what exactly we want to be doing. Okay, survey design considerations. I think, well, Kyle, you already talked about some of this. Yes, we need to get redshifts. Yes, the instrument has to be 10 times better than DESI as far as the light collection ability. And yes, tracer bias, sure, there are lots of trades that we can make here. Okay, but the universe has been very kind in providing compact galaxies. So this is really something when I go to bed every night, I'm just thankful that like, yes, the universe is at low redshift. It's given us all these galaxies that DESI's mapping right now, where we have these emission features that you don't even detect on Earth in the lab, but galaxies reprocess a lot of their energy into these forbidden transitions, and then we can easily measure redshifts for those galaxies. At higher redshift, we're even luckier. So there's the Lyman alpha feature, brightest feature in the universe. There we go. We can use that to map these galaxies above redshift of 2. And really, we could do this out to redshift of 7 straightforwardly if there was the case to do that. Okay, so the reference design, it made various trades around this just to get this 10x in figure of merit. And we have been taking some pilot data with the DESI instrument to see what these things look like. And so this is just an example of what some of these spectra look like and how we measure the redshifts of these. But the point is, you know, we've demonstrated we can do this. And as a targeted survey, meaning that we're pre-identifying the objects that we're looking at, we have a lot of flexibility as far as deciding, you know, what exactly we're observing. And so for DESI, in fact, these trades were made right up until a couple weeks before the survey actually started. You know, at that point, there were minor changes, but pretty major changes up until about a year before. Okay, so the SpecS implementation will upgrade 2 existing telescopes. So one of them is the Mail telescope in Kitt Peak, Arizona. This is the same telescope that DESI rebuilt once. And what we're proposing is we rebuild it again. And then it has a twin telescope in Chile, the Blanco telescope, currently hosts the dark energy camera. So these 2 telescopes, what we've discovered only in the last, 7 months, is that we can actually fit a much larger mirror into these telescopes. This is not true in possibly any other telescopes in the world, but these 2 telescopes, they're special. Again, the universe has been kind, or whoever built these things originally in 1972. So we can fit these much larger primary mirrors. We can build a new optical corrector to go with it, and then have a focal plane that's about 3 times larger than DESI at each site. And some spectrographs, just a few. Okay, this is that optical design. You know, at least, again, if we had this bag of cash, we had to build it today, this is what we would build. It's actually a quite elegant optical design to give us the field of view. It's lenses smaller than have been built for other telescopes, and they're all spherical surfaces. So for those of you who know about building telescopes and lenses, having spherical surfaces is just, it's cheaper, faster. Then there are some modest modifications that need to be made to the telescope mounts. And then at the focal plane, we want a lot more robots and fibers so we can multiplex more. This is a portion of the DESI focal plane with its 5,000 robotic positioners. So this has a pitch, a fiber to fiber spacing of about 1 centimeter. And the Spec S5 design makes them about 2.5 times smaller just so we can fit more robots into each focal plane. So this is just a picture of some of these prototypes that we've been building. And actually, they're in the building. So if someone wants to see them, we can show you. Maybe we should bring them down here. Okay. The current design, again, if we had this bag of cash and we were forced to start tomorrow, we'd build to print the existing DESI spectrographs, which are actually great. So in fact, if we were redesigning these today, they're so good, we wouldn't change anything. The only thing we might change are the detectors. So the plan here is to use these new multi-amplifier sensing detectors. They're essentially noise-free CCDs. And we do have the opportunity, again, if we don't have to build it tomorrow, that there might be a new CCD technology developed that could fill in. There's this one blind spot in redshifts that we have. We have to decide how much we care about it. But redshifts 1.6 to 2.0, it just happens to be much more expensive to observe. So you can build a very costly instrument that can observe those. That's what prime focus spectrograph has done. Or you can observe about 30 times longer, or you can try to get a germanium CCD. So those are kind of the options for that redshift range. Okay, status of Spec S5 today. So endorsed by Snowmass, P5, was presented to the HEPAP facilities subpanel recently. And actually this, is it Thursday? Thursday. I told you it's a fast moving field. We'll see what they have to say about that. We've requested a project start, so that would be CD0 in 2026. The construction project would be longer than DESI just because it's building more. So we're looking at a project in the mid-2030s. This would keep us on this curve where we've been making redshift survey maps that are 10 times larger every 10 years. So this is remarkable going back to the CFA redshift survey in 1983. We still seem to be on this curve. So if you could select exactly the galaxies you wanted at each redshift, my claim is that by 2043, if we stay on this curve, we'll have mapped all the linear modes up to redshift of 4. And then all detectable galaxies in the year 2061. So I like to ask people, figure out how old you'll be then. I'll be 94. Then I can retire. Okay, and then let me just close with this map of where we are in the Milky Way. And so this is just something else to be thankful of. There are probably some older, more advanced civilizations closer to the center of the Milky Way. Terrible place to try to observe the sky. So even though they might be way more advanced than us, they might have less of an understanding of cosmology than we are, because we live somewhere where we can actually quite easily make these maps. So I'll just end with the common phrase of carpe noctem. Thank you. And we have time. Okay. That's a hard question. Kyle gets it. Okay.
Thanks, both. So I'm a bit confused about the tracers that you guys are looking at, the tracers, because you were talking about dropouts and you were talking about Lyman alpha emitters, and I understand, which one is the tracer that you guys will be, targeting preferably in the Spec 5. And related to it is the fact that at least there were concerns a few years ago that these LAEs might have large selection effects. And so is this a concern or not?
So how about I start, do you go?
All right, fine.
Okay, so it's an excellent question about the tracers that are being selected for this high redshift range. And if you really paid attention, David and I kind of went back and forth calling them different things. So the reason we did that is because the default selection is a superset of basically all these techniques. So what we have as a template selection right now, or draft selection, is a broadband selection based on a U minus G, G minus R color cut. Another one based on a G band dropout. And then a third class that's based on colors observed through medium band imaging that we're in the process of trying to acquire. And that would be that would be a combination of LBGs, which is a breakout galaxy, a continuum-based galaxy where you get redshift through absorption features, and a combination and emission line galaxies where you see a strong Lyman alpha emission. That's the idea. Part of the benefit of doing this hybrid approach, I would hope, is to address some of the systematics that may be present in the choice of tracer. Specifically emission line galaxies at this redshift, the Lyman alpha line couples to the density field through neutral hydrogen. So that potentially modulates the emission line fluxes from this sample and may affect your redshift statistics rate. But by having this hybrid selection, it should give us a lot more information content on making these measurements.
I see. Thanks.
Yeah, and I'll just add to that. We'll almost certainly want to have different selections, even in the same redshift range, and we'll learn a lot in the coming years as far as what these look like, and yeah, I mean, I think there's a lot to learn here, but I should say it's history has told us we've done a good job of figuring out what these various galaxies look like, and compared to other techniques of mapping the universe, and I keep alluding to line intensity mapping, the galaxies that are so much easier and and you're really localizing each object, so it's qualitatively an easy population to work with. Let me just leave it there.
A quick question about the bag of cash next to you. How big is it? What is the current estimate of the cost?
So we did present a costing to HEPAP. That costing was based upon, again, if we had to build it today and scaling essentially the cost from DESI with no additional cost savings. For example, the robots, we're commercializing the production of robots. We're commercializing the production of what we can. That said, the number was about 500 million that we presented. I would hope that prior to CD1, when you need to define a cost envelope, we'd have a much better understanding of this. But that was a realistic costing.
So that's really interesting about what was Z equals 1.6 to 2. If you're going with the cheaper CCDs, it would cost 30 times more exposure to image that. So is there any thought about, well, how about we just don't do that? I mean, we just don't do 1.6 to 2, and what are the, what's the discussion around that?
Yeah, well, right now, the only project that's going to do that redshift range is PFS. For DESI, we do sample quasars in that redshift range. So quasars are special. They do have bright features you can see even at that redshift range, but that's really only for quasars, and they're very sparse. So if you wanted a dense sampling in that redshift range, right now it's very expensive, and only that one project has chosen to do that expense. What's that? Oh, Euclid will do it. That's right. Euclid will do it. Thank you. Euclid's not cheap either. Yeah.
What's the redshift range of Euclid? 0.9.
Roman will do some of it too, right?
Yeah. And so to clarify, when he said 30 times exposure, it really meant you had to observe with silicon-based detectors, getting absorption lines in the UV that are really hard and expensive. Whereas the germanium CCDs take you into the infrared and allow you to see the O2 emission line. Now, what's the limiting factor there is germanium CCDs don't exist yet. So that is what we're contending with.
Right. But if they did exist to give a slightly longer answer, I'm not sure we care that much about that specific narrow redshift range. Though if you had that capability, then you don't have any blind spots anymore. And so you do have this issue right now where you can do one of these redshift surveys. You have some number of objects where you just cannot measure a redshift. And it's likely that many of those fall into that window where you can't determine them. This would remove that blind spot. So I think that would probably be the more compelling reason if one did that.
I'm not seeing any other questions. Thanks, speakers again. So we have a coffee break now until 10:15. No, 11. Oh yeah, 45 minutes. 45 minutes. It's a 45-minute coffee break.
Oh yeah, all right. Yeah.
For those on the YouTube live, we will stop the stream and you can just click on the same URL later on and find the stream again. Thank you.